what we're now ready to do is actually go through the process of solving these equations. So let's start with a matter-dominated universe with W equals 0. And I'm going to do matter, radiation, cosmological constant, and curvature. And each of those basically follows the same set of steps. What I'm actually going to do is I'm going to show you slightly different ways of doing it in each case, but in principle the same steps can be done in each time, so you can pick whichever one you actually feel more comfortable with. So, for a matter-dominated universe, let's do the following. The fluid equation, E dot plus 3 A dot over A E plus P equals 0. But the equation state parameter P equals WE, so P therefore in this case is 0. There's no pressure from this non-relativistic matter. So this therefore very simply becomes E dot plus 3 A dot over A E equals 0. And you can just, if you want to, rearrange this and integrate it. I'll do that when I do radiation. But, you know, just a slightly even simpler thing to do in this particular case is you can rewrite this as the following. You can rewrite it as 1 over A cubed, right? Pull out a 1 over A cubed at the beginning, times 3A squared A dot E plus E dot A cubed. So essentially what I've done is I've multiplied top and bottom by A cubed in this case. This kind of looks a bit complicated, but this here, this bit inside the bracket, is just d by dt of EA cubed. Of course, this is equal to 0. So that tells you that the time derivative of EA cubed is equal to 0. Or that the product of E epsilon and the energy density times A cubed is equal to a constant. And in that case I can say E is just some energy density that I measure at the current time divided by A cubed. So that's how the energy density in a matter-dominated universe varies with time. And it's not at all surprising, because if I just think of this, you know, as a balloon, for example, or, you know, some gas, if I double the volume, or no, double the size of a side, sorry, you know, if I have a cube, I double the size of the side, it goes up by a factor of 2 cubed, which is a factor of 8. So in other words, the volume goes up, the density goes down. This is exactly just what you'd expect, very naively thinking about this. So now, let's assume that there's a matter-dominated universe and that omega m equals 1. So it's also flat. It really contains only matter and matter at the critical density. And then I can substitute into the Friedmann equation. And doing that, I get that A dot squared equals 8 pi g E naught over 3c squared times 1 over A. So in other words, what I've done to get that, because perhaps it's not completely clear, if I take the Friedmann equation itself here, A dot over A squared equals 8 pi ge over 3c squared. I substitute in 8 pi g over 3c squared E naught over A cubed. I then bring across the A from this side, and that's what gives me A dot squared equals 8 pi g E naught over 3c squared times 1 over A. And something, you know, you're still early in your education here, but something that's very common in astronomy is that things have power law solutions. So again, you can integrate this, and we'll do that when we look at radiation. If you prefer not to integrate this, you can guess a power law solution of the form A of t is proportional to t to the q. And then you can look at the proportionalities on this side and basically get a simultaneous equation in q, because it has to be consistent, right? Dimensionally, my powers of time have to all match. Okay? So, in this case, the left-hand side is proportional to a dot, right? So the differential of a dot is t to the q minus 1, and then that's squared. So it's equal to t to the 2q minus 2. And then the right-hand side is just proportional to t to the q minus 1. So when can 2q minus q minus 2 equal q minus 1? So the solution to that is when q equals 2/3. In other words, the Friedmann equation tells us for matter that a as a function of t is just equal to t over your current time to the power 2/3. And that's not, therefore, some sort of hand-wavy argument about the universe that's flat and matter-dominated will expand but slow down. This is now a quantitative statement of how a universe which contains matter and only matter is going to evolve in time.